Hello everyone and welcome to our first video on Unit 4.1, which will be on systems of equations in two variables. Technically speaking, we should say linear systems of equations in two variables, but I digress. The first thing we're going to talk about is what it means to be a solution to a system. In order to talk about that, let's define what a system of equations is. A system of equations is a collection of two or more equations involving two or more variables. So we say that a system is linear if all the variables in the equation are raised to the first power. Otherwise, it is a non-linear system of equations. And later on in your mathematical career, we start using this notation more frequently. So I'm going to try and introduce it now. This is a 2 by 2 system. In fact, it's a 2 by 2 linear system because we can see that all the variables are being raised to only the first power. And so it's a 2 by 2 system because it has two equations and two unknowns, x and y. The second one is a 3 by 2 system because it has three equations and two variables, x and y. And this is in fact a nonlinear system because of the x squared and the natural log of y. Those things immediately make it a nonlinear system. Versus this 3 by 3 system, three equations, three unknowns, x, y, and z. And this is a linear one because all the variables are being raised to the first power. But in this section, we're going to be purely focusing on 2 by 2 systems. So two equations, two unknowns, and they need to be linear. So now that we have that out of the way, let's talk about what a solution is. A solution to a two variable system is an ordered pair, x comma y, that satisfies all the equations in the system. So this is a two variable system. This is a two variable system. And if we plug in an x and y combo and it solves it, then it's a solution to both. Like if it solves it to both equations or all three equations in this case, then it is a solution to the system. Similarly, for three variable systems with an ordered triple, x comma y comma z, or a four variable system with an x comma y comma z comma w, and so on and so forth. So now we can do our first example where we determine whether or not the points 7 comma negative 1 and 4 comma 2 are solutions to the system below. So we'll start off with 7 comma negative 1. And what we're doing is we're checking to make sure that it solves both equations, i.e. you get a true statement when you plug it in. So this is our x value, this is our y value. So in the first equation, x plus y equals 6, we would get 7 plus negative 1. Does that equal? So I'm not sure yet. So I'm going to put a question mark over my equal sign. Does that equal 6? And yes, it does. It does equal 6. So then we'll check the second one because it's not enough to check one. So 2 times 7 minus 5 times negative 1, does that equal negative 2? And if you do that, you'll get 19. Does that equal negative 2? No, it does not. So even though this solved the first equation, it did not solve the second equation and therefore is not a solution to the system. It is not a solution to the system of equations. And then let's try 4 comma 2. Once again, that means that our x value is 4 and our y value is 2. So plugging it into the first equation, does 4 plus 2, does that equal 6? And yes, it does. You get 6 equals 6. That's a true statement. And then we'll check the second one. 2 times 4, it's 8, minus 5 times 2, just 10. That's negative 2. Does that equal negative 2? Yes, it does. So this is a solution. So 4 comma 2 is a solution where 7 comma negative 1 is not. And so before we go into the different solving methods, because being able to check whether something's a solution is great in theory, right? But how do we determine whether or not it's how do we find solutions instead of just being given to them? So one observation that can be made is that in a 2 by 2 system, and a 2 by 2 linear system, that is, every equation can be rewritten as in slope-intercept form, y equals mx plus b, right? You could just subtract x from this first one. You can subtract x, 2x from both sides and divide by negative 5, and you can get this into slope-intercept form. And as such, these systems represent two lines and their solutions are the intersection points. So that's what we're looking for. We're looking for where the two lines intersect each other. And in that case, if we're thinking about them as two lines, then there are three different possibilities. But in order to talk about that, we need to have some terminology to look at. And you don't need to have this terminology memorized. It's just for reference, and I would encourage you to reference it when you need. This is something that would be more important to have memorized maybe in Math 253, which linear algebra. That's when you'd probably want to have this memorized. This is just for us to talk about. A system is said to be inconsistent if the system has no solution. So that naming kind of makes sense. It's inconsistent, it has no solution. Oh, I forgot to highlight the definition. Then a system is said to be consistent if the system has at least one solution. When it has exactly one solution, a unique solution, we say that it is independent. Whereas if the system has infinitely many solutions, we say that it is dependent. So what do those all look like? Well, I've got this chart here to kind of look at all the different situations. So this first one shows two lines that are parallel. The blue line is 1/2 x plus 1, and the red line is 1/2 x minus 2. So the number of solutions here is none. There are none. As we know, parallel lines will never intersect, so there's no place where we have a solution. The other option would be that they intersect like this, in which case, so I've got the equations of the lines listed. This point right here is the solution, and there's only one. There's a unique solution, one solution. And the last one, and this took me a long time to write because this is the same line, but I had to do a gradient to make it into two different colors at the same time. But in this case, when you have a system where both lines represent the exact same equation, or both equations represent the exact same line, then what that would mean is that every point on this line is a solution because it will solve each equation because each equation is the same line. So in this case, we have infinitely many. Let me zoom back out. In this case, we have infinitely many solutions. So in terms of the definition 4.1.3 terminology, the first one is an inconsistent system because it does not have a solution. The second one has a solution, so it's consistent. And since it is one and only one solution, it is consistent and independent. And then the last one, there are infinitely many. So this does have solutions and therefore is consistent, but that means that it is dependent. So the solution type would therefore be, if you have no solution, then this doesn't make any sense. There is no solution. If the lines intersect, it's an ordered pair. If it's a consistent independent system, then there is an ordered pair, and in this case, that would be 2, -1. And then if you have infinitely many solutions, you have a consistent dependent system, then the solution type would be all points on the line in question, which is in this case y equals 1/2 x plus 1. That's one way to write it. So saying all the points on the line y equals 1/2 x plus 1, or we could say the ordered pairs x, 1/2 x plus 1. That would be your x, y. So a solution to a system is an ordered pair. In this case, you're saying that it's all the pairs where x is like your y values are dependent upon your x value. So whenever you plug in an x value, you get a corresponding y value on this curve. So that's another way to write the same thing. There are other ways that mathematicians have written it, and if you go on to linear algebra at some point, they might have you write it in completely different terminology, but that will be sufficient for now. Now, how do I know if I have an inconsistent system or consistent independent or a consistent dependent? Now, if you graph it, you can see it right away. But what would you do if you're going to try and find the solution algebraically? If it's an inconsistent system, the algebra giveaway is that when solving, you get a quote unquote false statement. Now, what do I mean by that? Something like quote unquote 2 equals -5, right? That is not a true statement. That is a false statement. 2 is not equal to -5. 2 is equal to 2. So that is a situation where you would know once you've done that and you get to a false statement, that means that the system is inconsistent. They're parallel lines and they don't have a solution. And then the algebra giveaway for a consistent independent is that you get a unique solution. If you get a unique X value and a unique Y value, you have a consistent independent system. They intersect at one point only. And the last one is what happens if you get consistent dependent? Well, when solving, you get a true statement. So something like quote unquote 10 equals 10. That's just a true statement. 10 is of course equal to 10. And so that kind of like, and that might seem weird at first. Why is that the algebra giveaway? And what we're going to be learning is that every method that we use to solve something, every algebraic method that we use to solve something, we're going to be doing things that do not change the solution set. So if I try and solve them with algebraic methods and I end up with a false statement, that means that there's no x value that would be true. And if I get a true statement, then I'm saying that it doesn't matter what x is. It's always going to be a true statement. And therefore, every x value will work, regardless of what x is. So we'll finish this video off with the first method of how to solve them, which is graphing. Um, so you could graph the system to figure it out. So we're going to solve the system 2x plus y equals 7 and x minus 2y equals 6. First and foremost, we're going to rewrite each equation in slope-intercept form so that we know how to graph it easy. So the first one, all you would need to do is just subtract 2x from both sides and get y is equal to -2x plus 7. And then the second one, you'd need to subtract x and then divide by -2, and you'll get y is equal to 1/2 x minus 3. Because you'll divide both sides by 2, you'll divide the x by the negative x by -2, that'll give you 1/2 x, and you'll divide the 6 by -2, which is where I get the -3. And so now the step 2 is to graph those lines and find where they intersect. So the first line, the blue line, has a y-intercept of 7 and has a slope of -2. So go down 2 over 1 and get the point 1 comma 5. And then I will connect those with a line like that. And then I'll do the same thing with the other one. It has a y-intercept of -3 and a slope of 1/2. Like that. And we see that they intersect right here at 4 comma -1. So the solution is 4 comma -1. Now, step 3, especially since we're drawing this by hand, we better be dang certain that it's the correct answer. So we'll check it in both. So I'll plug it into the first one. 2 times 4 plus -1. Does that equal 7? Yes, it does. And then 4 minus 2 times -1, does that equal 6? Yes, it does. So this is a solution. Now, keep that be that as it may, this method is valid. However, it's very susceptible to human error because we can't draw straight. I mean, I can draw a straight line with my tablet because it can do that. But as a human being, I can't draw a straight line to save my life. So how could I be certain that I get it exactly right? Like if I'm drawing it by hand, I might get a little bit off, and then I'm like, well, maybe it's like 3.5 comma negative 1.1. And so that's the thing we need to look out for. However, if you have a graphing tool like Desmos or a graphing calculator, go bananas because that can graph it perfectly. And that'll do it for this video. And I'll see you on the next one.